Hello everyone, welcome to the lecture series on computer architecture and organization. In this lecture, we are going to see about clusters, warehouse scale computers and other message passing systems. So this is the message passing multiprocessors. What is message passing? This is communicating between the multiple processors by explicitly sending and receiving the information. What is send message routine? A routine is used by a processor in machines with private memories to pass a message to another processor. What is receive message routine? A routine used by a processor in machines with private memories to accept a message from another processor. So clusters. So an important and relatively recent development computer system design is clustering. Clustering is an alternative to symmetric multiprocessing as an approach to providing high performance and high availability and is particularly attractive for server applications. We can define a cluster as a group of interconnected whole computers working together as a unified computing resource that can create the illusion of being one machine. The term whole computer means a system that can run on its own apart from the cluster. In the literature, each computer is a cluster and it's typically referred to as a node. So the four benefits that can be achieved with this clustering is that the first is absolute scalability. It is possible to create large clusters that far surpass the power of even the largest standalone machines. A cluster can have 10, hundreds, or even thousands of machines, each of which is a multiprocessor. And the second benefit is the incremental scalability. A cluster is configured in such a way that it is possible to add new systems to the cluster in small increments. Thus, a user can start out with a modest system and expand it as needs grow without having to go through a major upgrade in which an existing small system is replaced with a larger system. And the third benefit is high availability. Because each node in a cluster is a standalone computer, the failure of one node does not mean loss of service. In many products, fault tolerance is handled automatically in software. The superior price performance benefit is that by using these commodity building blocks, it is possible to put together a cluster with equal or greater computing power than a single large machine at very much lower cost. This is about this cluster configurations. In this literature, the clusters are classified in a number of different ways. Perhaps the simplest classification is based on whether the computer in a cluster share access to the same disk. This figure, that is the standby server with no shared disk, shows a two-node cluster in which the only interconnection is by means of a high-speed link that can be used for message exchange to coordinate this cluster activity. The link can be a LAN that is shared with other computers that are not part of the cluster, or the link can be the dedicated interconnection facility. In the later case, one or more of the computers in the cluster will have a link to a LAN or WAN so that there is a connection between the server cluster and remote client systems. Note that in the figure, each computer is depicted as being a multiprocessor. This is not necessary but does enhance both the performance and availability. In the simple classification depicted in this figure, the other alternative is the shared disk cluster. So in this case, there generally is still a message link between the nodes. In addition, there is a disk subsystem that is directly linked to multiple computers within the cluster. So in this figure, the common disk subsystem is a RAID system. The use of RAID or some similar redundant disk technology is common in clusters so that the high availability achieved by the presence of multiple computers is not compromised by a shared disk that is a single point of failure. So this is about this clustering methods. A clearer picture of this range of cluster options can be gained by looking at this functional alternatives. So this table that provides a very useful classification along the functional lines. So however, if you see here, however, the failures are managed by a cluster depends on the clustering method that is used in the previous table. In general, two approaches can be taken to dealing with this failure. That is the highly available clusters and fault tolerant clusters. A highly available cluster offers a higher probability that all resources will be in service. If a failure occurs, such as the system goes down or a disk volume is lost, then the queries in progress are lost. Any lost query, if retried, will be serviced by a different computer in the cluster. However, the cluster operating system makes no guarantee about the state of partially executed transactions. This would need to be handled at the application level. And the next is the fault tolerant clusters that ensures that all the resources are always available. This is achieved by the use of redundant shared disk and mechanism for backing out uncommitted transactions and committing completed transactions. The functions of the switching applications and data resources over from a failed system to an alternative system in the cluster is referred to as this failover. A related function is the restoration of applications and data resources to the original system once it has been fixed, and this is referred to as failback. Failback can be automated, but this is desirable only if the problem is truly fixed and unlikely to recur. If not, automatic failback can cause the subsequently failed resources to bounce back and forth between the computers, resulting in performance and recovery problems. A cluster requires an effective capability for balancing the load among the variable available computers. This includes the requirement that the cluster must be incremental scalable. When a new computer is added to the cluster, the load balancing facility should automatically include this computer in scheduling applications. Middleware mechanisms need to recognize that services can appear on different members of the cluster and may migrate from one member to another. So, in some cases, effective use of a cluster requires executing software from a single application in parallel. So, this lists three general approaches to the problem. That is, one is the parallelizing compiler, and the second thing is parallelized application, and the third is parametric computing. So, what is parallelizing compiler? Coming to this point, it determines at a compile time which parts of an application can be executed in parallel. These are then split off to be designed to different computers in the cluster. Performance depends on the nature of the problem and how well the compiler is designed. In general, such compilers are difficult to develop. And the second thing is parallelized application. In this approach, the programmer writes the application from the outset to run on a cluster and uses message passing to move data as required between the cluster nodes. This places a high burden on the programmer but may be the best approach for exploiting clusters for some application. Coming to this parametric computing, this approach can be used if the essence of the application is an algorithm or program that must be executed a larger number of times, each with a different set of starting conditions or parameters. A good example is a simulation model which will run a large number of different scenarios and then develop statistical summaries of the results. For this approach to be effective, parametric processing tools are need to organize, run, and manage the jobs in an effective manner. So this figure shows about a typical cluster architecture. The individual computers are connected by some high-speed LAN or switch hardware. Each computer is capable of operating independently. In addition, a middleware layer of software installed in each computer to enable this cluster operation. The cluster middleware provides a unified system image to the user known as the single system image. The middleware is also responsible for providing high availability by means of load balancing and respond to failures in individual components. A cluster will also include the software tools for enabling this efficient execution of programs that are capable of parallel execution. So this is about this common implementation of the cluster approach, that is the blade server. A blade server is a server architecture that houses the multiple server modules, which is called as blades, in a single chassis. It is widely used in data centers to save the space and improve system management. Either self-standing or rack-mounted, the chassis provides a power supply and each blade has its own processor, memory, and hard disk. An example of this application is shown in the figure. The trend at large data centers with substantial banks of blade servers is the deployment of 10 Gbps ports on individual servers to handle the massive multimedia traffic provided by these servers. Such arrangements are stressing the on-site Ethernet switches needed to interconnect large number of servers. A 100 gigabits per second rate provides the bandwidth required to handle the increased traffic load. The 100 gigabits per second Ethernet switches are deployed in switch uplinks inside the data center, as well as providing inter-building, inter-campus, wide area connections for enterprise networks. So this is how the clusters are compared to SMP. Both the clusters and this symmetric multiprocessors provide a configuration with multiple processors to support high demand applications. Both solutions are commercially available, although SMP schemes have been around for longer. The main strength of the SMP approach is that an SMP is easier to manage and configure than a cluster. The SMP is much closer to the original single processor model for which nearly all the applications are written. The principal change required in going from a uniprocessor to an SMP is to the scheduler function. Another benefit of the SMP is that it usually takes up a very less physical space and draws less power than a comparable cluster. A final important benefit is that the SMP products are well established and stable. Over the long run, however, the advantages of the cluster approach are likely to result in clusters dominating the high performance server market. Clusters are far superior to SMPs in terms of incremental and absolute scalability. Clusters are also superior in terms of availability because all components of the system can readily be made highly redundant. So that's all about this. Thank you.